All right, so today we're going to turn our focus to logarithmic functions and graphing those guys. And what we'll discover is that logarithmic functions are nothing more than inverses for exponential functions. We'll use that idea to help us graph. Okay, so quick review here, and what will help us lead into a logarithmic graph is, let's go ahead and graph this exponential function. All right, you did this a bunch in your homework from before. So go ahead and take a second and get this in. Stop the video. When you're done, start it back up and make sure you got it right before we move on. All right, and you should have this, the table for your 2 to the x, right? So again, hopefully this is getting to be kind of second nature. You've done this so much that these xy values hopefully are coming pretty easy to you now. But anyway, now I said before that logarithmic functions are basically inverses for exponential functions. And so in the second grid that you have there in your notes, here's what I mean by inverses. So we know that when you're solving equations, inverse operations undo each other. Inverse functions, kind of the same deal where they kind of undo each other, but they're kind of opposite functions. And what I mean by that is, for inverse functions, inputs become outputs, outputs become inputs. In other words, to come up with the inverse function for y equals 2 to the x, you'd want to switch the y and the x. So this x would, or this y would become x, this x would become y, and you would want to try to get y by itself. We still want the outputs to be over here, to be all by themselves. So let's say we did that. Switch those around, and now we want to get y by itself. Well, I would have to pull that y down out from an exponent. In order to do that, I'd have to rewrite using a logarithm, right? So base stays base, the exponent base is 2, so the log base is going to be 2. And the other two place switch a root. So the x would come over here next to the log, and y would be on the other side of the equal sign. And we would have essentially gotten our y by itself and created our inverse function of log base 2 of x. Okay? Log base 2 of x is the inverse function of 2 to the x. All right, that's great. How does that help us graph? Well, since we switched the x and the y and solved the function for y to get the inverse function, what that means is that for the points for the logarithmic function, all we've got to do is switch the x and the y coordinates for the points of the exponential function. So in other words, we're going to make another table here, and we're going to make these the y's and these the x's. Just switch them around. So we get 1/4 common negative 2, 1/2 common negative 1, 1, 0, 2, 1, 4, 2. And we would go graph those points. So 1/4 common negative 2, 1/2 comma negative 1, 1, 0, 2, 1, 4, 2. And so the logarithmic graph will look like this. Will look like this. Okay? And we've just flipped the exponential function over this over a line, a y equals x line. You don't have to worry about that. But there you go. That's the logarithmic function. This is what you should have in that second grid. I put them together so you can kind of see how they work, but that's it. Now, take a look at how this graph is a little bit different. The exponential graph, the blue graph, kind of levels off and doesn't want to touch this horizontal line at 0. The red graph, or the logarithmic graph, doesn't seem to want to touch this vertical line at 0. Now, a vertical line would have a different equation than a horizontal line, but we're basically still going to have an asymptote because the graph doesn't want to cross that value. That asymptote would be at x equals 0. A vertical line has an x equals equation. Right? The domain. The domain will is still the same thing. It's the x-axis. It's left or right. You know, where does this graph go? Does this graph extend to negative infinity and positive infinity? Left and right. The answer to that question is no, it doesn't. Again, the graph kind of wants to stop right here. We're at 0 on the x-axis. So the domain has to start just after 0. Now, it does extend to positive infinity in the other direction. So 0 to positive infinity. The range. It does go down to negative infinity in the y direction. And the graph will eventually get to positive infinity in the y direction. It's just going to take a little while. So if you take a look, some things are just sort of flip-flopped. Instead of y equals, x equals for our asymptote. The domain is now the range, and the range is now the domain. And that just kind of follows along with this whole idea of inverses, flip-flopping things. Okay? So anyway, that's your introduction to a logarithmic graph. So logarithmic functions, again, to summarize here, they're inverses of exponential functions. They're going to have a vertical asymptote instead of a horizontal one. And the steps to graph is that we're still going to make a table for exponential parent functions. And then we're going to make the chart for that. We're going to flip-flop the x's and y's. We're going to switch the x's and y's for our coordinates. Graph those points. And then if there is a shift after that. All right? So let's bring this all together just in having to graph a logarithmic function. Y equals log base 3 of x. The first thing you have to realize is that the exponential parent function for log base 3 of x is 3 to the x. Right? We're still going to use the same base for our exponent and then raise that to the x power. Right? And again, you did this a bunch of times in your homework, so hopefully these values are pretty quick to get to. But if you plug in negative 2 for x, you're going to get 1/9. You plug in negative 1 for x, you can get 1/3. This is going to be 1, this is going to be 3, and this is going to be 9. However, for our log base 3 points, we're just going to change the x and the y. So this is going to become 1/9 comma negative 2, 1/3 comma negative 1, 1 comma 0, 3 comma 1, 9 comma 2. And now we want to plot those points. Right? So 1/9 negative 2 would be here. 1/3 comma negative 1 would be there. 0 comma 1. 3 comma 1. And then 9 comma 2. And so there's your logarithmic graph. There is no shift here, so we don't have to worry about shifting it, so we can draw it in as a solid line. But then our characteristics, the asymptote. This graph still does not seem to want to touch the vertical line of x equals 0. So that becomes our asymptote. The domain, again, since it doesn't want to go past 0 on the x-axis, the domain starts at 0 and then goes out to positive infinity. The range is still going to be negative infinity to positive infinity. Okay? All right. Take a second and see if you can't get the graph for this logarithmic function. I'll give you a nudge here. Remember that the exponential parent function for this is going to be the same base, which is 4, to the x power. Right? So go ahead and get that in. Stop the video. Give it a shot. Start it back up. I'll show you the graph and make sure that you're doing this correctly. And so your graph should look something like this. Your table for your exponential parent function. Negative 2 comma 1/16, negative 1 comma 1/4, 0, 1, 1, 4, and 2 comma 16. Switch those x and y's to get to your logarithmic table. Right? If it's helpful, label them. And then, so 1/16 comma negative 2, 1/4 comma negative 1, 1, 0, 4, 1, and 16 comma 2. Plot those points, draw your graph, and there you go. It's still not wanting to cross the x equals 0 line, so that's your asymptote. Domain still 0 comma infinity. Range negative infinity to positive infinity. Okay? All right. Well, we saw when the base of the exponent was a fraction instead of a whole number, we sort of switched from a growth model to a decay model. we ought to take a look at what a logarithmic function would look like if the base was a fraction instead of a whole number, right? So here, log base 1/2 of x. It's the same process. We're still going to make our table for our exponential parent function, which would just be the same base, which is 1/2 to the x power. When we use -2, -1, 0, 1, and 2, again, you did this a couple of different times in your homework, so hopefully you understand that when you plug -2 in for x, we flip that over and square it, and we get 4, then 2, then 1, 1/2, and then 1/4. Okay? For your logarithmic table, switch them around. 4, -2, 2, -1, 1, 0, 1/2, 1, 1/4, 2. And we want to plot those points. So 4, -2, 2, -1, 1, 0, 1/2, 1, 1/4, 2. And so you can kind of see that it's still not going to want to cross the vertical line of x equals 0, but it does kind of flip around and I don't know how you want to look at it, but kind of ski down, sort of, right? Just flipped over from the previous log functions. So our asymptote is still going to be at x equals 0. Our domain, again, still doesn't want to cross 0 on the x-axis, so 0 to infinity. And the range would go -infinity to +infinity. All right? So flips around, kind of like what the growth and decay models do. All right. Now that we've seen one of those, let's take a look at some shifting. Okay? To graph this logarithmic function, it's still the same process. We still want to get a table in for our exponential parent function, which is going to be here, the log base is 3, so it's still going to be 3 to the x. We've seen a lot of these tables, so a little bit quicker. -2, 1/9, then 1/3, then 0, 3, and 9. Okay? Now, the logarithmic table would just be these flipped around. I made this a 0. I meant to make this a 1. Sorry. So 1, 0, 3, 1, 9, 2. Okay, but we are going to have to shift. There is a number in here that's going to have a shift the logarithmic function. And so this is the log function that we're going to graph is actually going to be a bit of a parent function as well. So here, is the parent function, the logarithmic parent function. And remember that any time, whether it was an absolute value, as a matter of fact, the absolute value would have looked like this, right? When we added something to the x in the absolute value bars or in quadratics, we always added or subtracted the h, right? Even for our exponentials, when we added or subtracted something to the x in the exponent, we called it h. Same thing here. We're adding a 2 to the x in this logarithmic argument, and so that makes this guy h. And so h stands for horizontal. This is going to provide a horizontal shift, and just like every other one of these examples, it's going to provide a horizontal shift in the opposite direction in which you probably are thinking about it, right? So we need to shift everything left to instead of right to. No problem. We just take all these points and shift them left 2 spots. So this guy goes here, this guy goes here, this guy goes here, and then here, here. And the imaginary wall kind of gets shifted back as well. Now this graph doesn't seem to want to cross -2 on the x-axis. So our asymptote would be at x equals -2. If that's the case, then that means the domain doesn't want to start until after -2 and then go out to positive infinity. And the range still stays negative infinity to positive infinity, no problem. Okay? So that's an h. We want to shift the opposite direction. All right? Versus something like this. Now, this -3 is not in parentheses. And so, therefore, that -3 is not going to be, it's actually being subtracted from the entire function, log base 2 of x. Okay? And sorry, if these are a little bit different than what are in your notes. I am doing some different functions than what are in your notes. This 7 is the same. 6 was a little bit different. Sorry, I didn't make that clear, but that's okay. Change the functions to match mine so you get the right examples in. Okay? So anyway, this -3 is not being subtracted from the x. It's being subtracted from the entire function log base 2 of x. So that no longer is h. This is where k always sat. So this -3 is going to be k for this logarithmic function as well. That means we're going to have a shift, but it's going to shift like a kangaroo, right? It's going to be a kangaroo shift, where it's going to shift either up or down. And like all of the k's before, we want to shift down 3, right? So to make that happen, we still need our exponential parent function, which is the base is 2, so 2 to the x. So our exponential table, which is starting to get kind of redundant. But there you go. Now for your logarithmic function, we want to flip that around. And so we can plot those points and draw in the logarithmic function, but it's going to be more of a logarithmic parent function. So we want to dot that in. And since this -3 is a k, then we want to shift everything down 3. So we go down 3 here, down 3. Oh, this guy, forgot, skipped one. 1, 2, 3, down 3 here, here, and here. And so now we're going to draw in our actual, which is a little bit off, but that's okay, our actual logarithmic function there. Okay? We're looking for that asymptote. Again, it doesn't want to cross the same x value as the original logarithmic function, so x equals 0 is the asymptote. The domain is still going to be 0 to positive infinity, and the range, you guessed it, still going to be negative infinity to positive infinity. Okay? All right. Here's another one for you, but this time we've got a fraction for our base. So I'm going to let you graph this one. Stop the video, start it back up, and see if you graphed it correctly. Okay, there you go. The logarithmic table should be 9, -2, 3, -1, 1, 0, and the third one, 1/9, 2. And because this k is -2, we want to shift all of our points down 2 spots. Okay? So there you see the logarithmic parent function in the dotted green, and then the actual function would be in the blue. Okay? Asymptote still going to be x equals 0, the domain 0 to positive infinity, the range negative infinity to positive infinity. Piece of cake, no problem. Okay? I got one more that I think you should see, where it's going to have a couple of shifts for you. So stop the video, get this one in, and make sure that you're shifting correctly, and then you'll be ready for your homework. And this graph should look like this, right? Just do your 3 to the x, flip-flop those points for your logarithmic function, 1/9 comma -2, 1/3 comma -1, 1, 0, 3, 1, and 9, 2. And then hopefully you shifted left 3, up 5 for your horizontal and your vertical shift. Okay? If you didn't get that, you don't understand why not, come in and see me during STAR. We will figure it out. Right? But for now, homework out in Canvas. Get that knocked out.